Anybody have any questions, first of all, that came up during all your studying over break?
When was our last class?
So I don't know when our last class was, but what we've been talking about is how to go from any kind of beam, like any kind of load profile on a beam, and calculate the stresses due to the shear force and the tension and the bending moment, or so we thought. So now we're going to talk about horizontal distributed loads. And relatedly, non-horizontal beams. Okay, so up until now, we've done things like this. You might have a beam like this that has some like complicated distributed load, or we've done ones like this, or maybe you have a distributed load like this. But what these have in common is that the distributed loads are always perpendicular to the long axis of the beam, okay? So all distributed loads I guess perpendicular to the beam's long axis. But that doesn't have to be the case. So for example, consider something like this. Where you have a bar just hanging from a pin joint. So let's say that this is 1.5 meters long, and let's say that the weight is 6,000 newtons. Okay, so say that we wanted to calculate the stress inside this beam. A free body diagram, you'd have force upward applied by the pin that's keeping it from falling of 6,000 newtons. But what would this weight force be doing? Well, the way that we tend to treat it so far, you know, like in statics problems, is we tend to think of it as concentrated at the center of mass. But if we're calculating the stresses, we have to treat it as a distributed load. So what this really is a downward distributed load of 6,000 newtons divided by 1.5 meters. So you end up with a distributed load like this of 4,000 newtons per meter. And now if we wanted to calculate the internal loads, we'll use a coordinate system with the x-axis pointing along the long axis of the beam like we've always been doing. So this will be x, y will be this way. And so imagine it rotated. And now you have a problem where there's a 6,000 Newton load this way, and then there's a distributed load to the right of 4,000 newtons per meter. Okay, so how many important points do we have on this beam? Just two, just the two endpoints. So 2 important points. So that means 1 cut. And this cut has to represent all x values between, you know, the beginning and the end, so between 0 and 1.5. We have a 6,000 Newton force here. This length is x. We have the tension, the shear force, and the bending moment, and then we have that distributed load. I guess I'll do this in 2 steps. Okay, so 4,000 newtons per meter going to the right. But now that we've chosen what body to isolate, now we know it's okay to treat that distributed load as a point force. So I'm going to rewrite this free body diagram. 6,000 newtons that way. The internal loads like this. And now we have a horizontal force pointing to the right. I'm going to draw it like this, but basically it's just a force going to the right, acting at the center of mass of the beam, and its magnitude is equal to 4,000 times x, right? Because that's what we do with these. I mean, this is a, how do we know that? Yeah, I guess it's a little hard to picture these as shapes anymore. So I guess maybe that's just something, just you're going to have to remember that we're going to treat these horizontal distributed loads as if they act at the center of mass of the object, okay, of the isolated object. So this is going to be 4,000 x. All right, and now we'll go to Newton's laws and think about what this, you know, what's going to change now that this force is going to the left and going to the right instead of down. So for Newton's second law, we have negative 6,000, 0. For the horizontal distributed load, we have positive 4,000 x, 0. Then we have P negative V is equal to 0. And so the shear force is 0, but the tension this time is the interesting one. That's equal to negative 4,000 x plus 6,000. And now the rotational equation, calculating the moments about that left endpoint. Does the 6,000 Newton force produce a moment? No. Does the 4,000 x produce a moment? Well, remember, this is acting, even though I drew it like it's acting like its line of action goes right through that endpoint. So that's not going to produce any moment either. So the only moments that we have are the bending moment, that couple, minus Vx, V is equal to 0, so M is equal to 0. Okay. And so up until now, we've always had the tension be pretty simple, and the shear force and the bending moment are the candidates for being, you know, sort of complicated functions. Now, in this example I just did, these two are 0 the whole way, but the tension starts out at positive 6,000 and drops down to 0. And if you think about what this says about the internal loads, it makes sense that up at the top, elements in that beam are supporting the entire weight of the beam that's hanging down below it. So you'd get your high values up near the pin. And then as you get down towards the bottom, the little pieces of metal here are barely holding up any weight at all. And so those are, as you get closer and closer to the end, those are approaching 0 for tension. Okay. Okay, so there are two things to notice here. First, a distributed load directed along the beam's axis doesn't produce any bending moment. So remember, like when we dealt with distributed loads that are perpendicular to the beam's axis, those are acting at x over 2 or x over 3 or, you know, some horizontal location. And that location is factored into calculating what the moment is that's produced by that distributed force. These don't produce any moment because their line of action goes right through the pins. In fact, and you don't have to write this down or anything, but you could have horizontal distributed. So imagine that we neglected the weight here. You could get a profile that looked like this by having something with friction rubbing against the side of that beam. You can imagine that, right? And that actually would produce a little bit of a moment, depending on how thick this beam is, right? Because it's offset by, say, a centimeter or some small distance from the axis between the... but mostly, we're going to be using these horizontal distributed loads as representations of weight. And the weight... the distributed load representing the weight goes right between the two endpoints, and it doesn't produce any moment. Okay, so we'll just, and even if you did have it because of friction on the surface, say that moment arm was 1 centimeter or whatever, it's not going to be a very big moment, right? Because that moment arm is so small. And so we're just going to treat it like it never produces any moment. Okay, the second thing to notice is you can treat any distributed load as a vector distributed load with horizontal and vertical components. So if you look back at this example, so you can think of this, this distributed load. Let me look at this picture. This distributed load, you can think of that as a distributed load vector with a horizontal component of 4,000 newtons per meter and a vertical component of 0. Okay? And then you just, whatever those two components are, you use the rules of the horizontal distributed load for the horizontal component, and you use the rules for the vertical distributed load for the vertical component. Okay, so here is an example of, so this is where it's going to be really useful. And let me, before we do this example, let's, no, I must have put it there in my notes for a reason. I'm going to trust myself. Okay, so here's the example. So let's say you have a beam resting against a wall connected to a pin joint down here. Let's say that this angle is 30 degrees. And let's say that the length is 4.8 meters. Let's say the mass is 2,000 kilograms. And say that we want to calculate the tension as a function of the location along the length, the shear force, and the bending moment. Well, the first step is we want to calculate that reaction force. This is a force vector. I'll call that RA. What's the direction of the reaction force at the top? It's going to be the left, yep, perpendicular to that wall, toward the chosen body, away from the contacting body. So I'll call that RB, I guess. And now that we've chosen the body to isolate, we've chosen to isolate the whole body, we can treat that distributed weight as a point force. Question, Mito?
Oh, I thought that was like a fixed joint.
Oh, okay. That's just leaning against the wall up there. Okay, so what's the weight? 2,000 times 9.81, so 19,620. Newton's second law says RA plus 0 negative 19,620 plus negative RB 0 is equal to zeros. And the rotational equation, calculate the moments about A. So this horizontal distance is 2.4 times the cosine of 30. And so you get a total moment there of negative 40,779.4. There's no moment produced by RA, and then there's a moment produced by RB of positive 2.4 RB. And, you know, you could have written this out as a table if you don't like sort of eyeballing it, thinking of it as rotations to get the directions and stuff. You can totally do the table and calculate those moments as cross products. Okay, so what do we get? We calculate that RA is equal to 16,991.4. And RB is equal to, RAY, I didn't write, is positive 19,620. That's RA. RB is positive 16,991.4. And so now we can write the full free body diagram like this. We have a force vector here of 16,991.4, y of 19,620. Up here we have, I'm going to write this as a vector, and you'll see why in a second. So we have a vector of negative 16,991.40. And then we have a distributed load that can be represented as a horizontal and vertical component of 0, negative, okay, so so what's the distributed load? I should have drawn this differently. Let me draw it like this first of all. So right now, I mean, this distributed load is just entirely vertical, right? What's the magnitude of that distributed load, or how do we calculate it? Well, we know that it's a total force of 19,620. It has a length of 4.8. So as a distributed load, that's going to be 19,620 divided by 4.8. And so you get a value of 4087.5. Okay. And
like find that out when you go to text only, you know, just leave it at this for now.
Well, if you want to represent it as a distributed load, you have to, I guess you have to be clear about how you're representing it. That's why with these distributed loads, I always put in the units so that you can see when I've started writing it. Like, there'd be nothing, I mean, if you wanted to represent that in terms of the entire force, that would be okay with me. But then it wouldn't be newtons per meter. It would be, you know, 40,000 whatever newtons. And now I'm going to represent this, instead of thinking of it as just a vertical distributed load with this magnitude, the way we've been doing it, I'm going to rewrite this as, and now this is the part that's new, I'm going to treat this as a distributed load vector. What's the horizontal component of this distributed load vector? 0. And what's the vertical component? Yep, negative 4087.5. And I always write the units in here to try to keep myself from getting confused. Okay, so we have that distributed load vector, and we still have these two force vectors, 16,991.4 and 19,620. And up here we have a vector of negative 16,991.4 and 0. Any questions up until this point? Okay, so we have these all expressed in vectors, but we know that what we want to do now is we want to re-express these vectors. And the vectors I'm talking about are two force vectors and one distributed load vector. In a coordinate system with the x-axis along the beam's long axis. So why do I want to do that? Yep. Yeah, exactly, because that's just the coordinate system that we have to use to calculate the internal loads. Okay, right now we have it in, you know, like if we did it, I guess I'll erase this in a second, but if we didn't re-express these vectors in a new coordinate system, we'd be trying to do our internal load calculation with a force vector like this, a force vector like this, and a distributed load vector like this. And our approach to internal loads just doesn't work with those orientations. Okay, so how are we going to re-express those vectors? Rotation matrices. So we do that by multiplying each vector by a rotation matrix. I haven't talked about this yet, have I? In this class, rotation? In statics, but not in this, okay. So, okay, so here is the idea for rotation matrices. So if you have a vector v expressed in coordinate system A, and you want to express that vector in coordinate system B, multiply or let me say it like this. Calculate QV where the rotation matrix Q has columns that are the coordinate system axes of A expressed in B. Okay, so in other words, if this is your coordinate system, like for example, if this is your coordinate system A, and this is your coordinate system B, and in this coordinate system, the vector V is equal to, let's say, 1, 1. Expressed in coordinate system A, then the rotation matrix to go from, like, to re-express it in coordinate system B is this way. So Q has columns let's see, Q has columns that give A axes in the B coordinate system. So let's say that this, okay, so let's say that this is 45 degrees, okay? This dotted line is lined up with the x-axis here. Okay. So what is, so in coordinate system B, give me a representation of the x-axis of coordinate system A. Okay. So that means that okay, so this is our coordinate system B. Okay. We're trying to represent this axis, right? That's the x-axis of this is the x-axis of coordinate system A, and this is the y-axis. What are the, if, so this angle is 45 degrees. This angle is 45 degrees. How would we represent the x-axis? Yeah, it's going to be cosine of 45 and then negative sine of 45. So we're going to have 0.7071, then negative 0.7071. And I'll write it in 3 dimensions. And then what about the y-axis? How would we represent this y-axis in the red coordinate system? It's going to be 0.7071, 0.7071, 0. And then the z-axis, well, we're rotating about the z-axis, so that's going to stay unchanged. All right, so Now QV is 0.7071, negative 0.70710, 0.7071, 0.70710, 001. We're multiplying that by this vector v, which is 1, 1, 0. And if you do that multiplication, you get what's that, 1.4, yeah, 1.412, 0, 0. Yeah. So now look at this again, and does it make sense that if this is our vector expressed in this coordinate system, so v is like this, right? This is v. If it's 1, 1 in this coordinate system, right? Does it make sense that it would have a value of 1.41 or whatever in this coordinate system? Yeah, it makes sense, right? This is pointed in, okay. I feel like that went really roughly. Okay, good. That's not usually how you have to calculate these rotation matrices. So most of the time, you can just use this formula or these formulas. To express in a coordinate system rotated theta degrees counterclockwise about the z-axis, your rotation matrix is going to be cosine of theta, sine of theta, 0, negative sine of theta, cosine of theta, 0, 0, 0, 1. To express in a coordinate system rotated theta degrees counterclockwise about the x-axis. Q is equal to 1, 0, 0. And then the second row is 0, cosine of theta, sine of theta. The last row is 0, negative sine of theta, cosine of theta. Yeah, they're both counterclockwise. They're both, everything's according to the right-hand rule. So counterclockwise if your thumb is in the direction of the axis. And then the last one, to express a vector in a coordinate system rotated theta degrees, again counterclockwise, so again according to the right-hand rule, about the y-axis. Now remember, the y-axis is always the one who has to be the smart guy. Like it's always got to throw some little wrinkle in everything, you know? The y-axis is always a pain in the ass. It's always been that way, ever since its birth. Okay, so the Q for rotation about the y-axis, it's almost the same as these. It almost follows that formula, but it's cosine of theta, 0, negative sine of theta. So the negative comes in that top row, and then 0, 1, 0, and then sine of theta, 0, cosine of theta. Any questions about that? Okay, so now we're going to go back to the example. And I'm going to write the beam this way. So here's what we have. We have a force on the left side, but in this, okay, so look at what I'm doing here. All that matters is, like mathematically, all that matters is what the components are in the coordinate system we're using. So whether I draw this horizontally or draw it vertically or draw it in between, that doesn't matter. All that matters is the components, okay? So notice that if I lay this flat, the coordinate system we're using, like if it's at an angle like this, the coordinate system is like this, right? If I picture this lying flat, then the x-axis is rotated a little bit down and the y-axis is rotated a little bit to the right. So that's all I'm going to do here is draw it where the beam is flat and the coordinate system is rotated like this. But those values are still the same. I haven't done anything mathematically yet. We're just looking at it in a different way. So here we have a vector of 16,991.4, 19,620. Over here, we have a vector of negative 16,991.40. And for the distributed load, whoops, that should be drawn rotated too. We have 0, negative 4087.5 newtons per meter. Okay, these are all forces, so these are all newtons. And we want to re-express in this coordinate system where, so from that original drawing, we know that, so we're talking about rotating it counterclockwise 30 degrees. Okay. And what axis do we want to rotate it about? Yep. So we want this to be, so theta is equal to positive 30 degrees about the z-axis. So the rotation matrix is cosine of 30, sine of 30, then negative sine of 30, cosine of 30, and then 0, 0, 1. Yeah, because the z-axis is pointing out of the page at us, and our thumb is pointing in that direction. So that's a positive rotation about z. And so numerically, that gives us 0.866, 0.50, negative 0.5, positive 0.866, 0, and then 0, 0, 1. Now we're going to multiply each of those loads by this matrix. Remember that this has to be a left multiplication. Okay, so we have one force. If we go 0.866, 0.50, negative 0.5, 0.866, 0, 0, 0, 1, times that force RA, which is 16,991.4, 19,620, and then 0z. We get a new force vector in this rotated coordinate system of 24,525, and then the y value is 8,495.7, and the z is 0. For the second load, we get, so I'm not going to keep writing this, but we have Q multiplied by this is the one at B, so this is negative 16,991.400, and we get a value, so we get a value here of negative 14,715, a y component of 8,495.7, z component is 0. What are the units on all of these so far? These are all newtons so far. We haven't done the distributed load yet. And then the last one is the distributed load. So we're going to multiply Q times our distributed load of 0, negative 4,087.5, 0. Remember, this is newtons per meter. And we get a distributed load of negative 2,043.8 newtons per meter, negative 39.9 newtons per meter, and then 0. And so I'll just write the final free body diagram, and then next time we'll finish up this problem and do the internal loads. So the complete free body diagram in the rotated coordinate system there's the beam. Over here we have a force vector of 24,525, that's newtons, and positive 8,495.7 newtons. Over here we have a force vector of negative 14,715, positive 8,495.7, I guess, and those are newtons. We have a horizontal distributed load that's in the negative x direction, so I guess I'll write that as a distributed load pointing to the left with a value of a magnitude of 2043.8 newtons per meter. And then finally a distributed load, the negative says that one's pointing down, and the magnitude of that is 39.9 newtons per meter. Okay, so now we're ready to do the internal load calculations, and after that we'd be ready to do the stresses. Okay. Any questions? All right, we'll keep going with that next time.